So in a previous video, we talked about using the ratio test to determine the interval and radius of convergence of a power series. Here we'll pick up the pace a little bit and we'll check out a few more power series and we'll try to find their radius and interval of convergence. So for the power series that we see here, this one's based at 1, right? X minus where the series is based is always what we're going to see with inside that set of grouping symbols. But for this particular power series, we look at it, we hopefully realize right away that it's not related to a geometric series because there's way more instance than just this k, because k is also used several times in the rule for producing coefficients. When you're in a situation like this is the sort of place where you're going to want to try to use the ratio test to determine your interval and radius of convergence. So the ratio test is going to be the limit as we approach infinity of a sub k plus 1. So if I bump this into the numerator, this x minus 1 to the k into the numerator with the 10 to the k, and then add 1 to all the k's, you're going to get what I have within this first fraction being written here. And then I would have to divide by a sub k. Well, rather than dividing by a sub k, we'll multiply by the reciprocal. And there's a ton of cancellation that happens with this particular series. So we'll deal with the 10s first. I have k plus 1 factors of 10 here. I only have k factors of 10 here. I've got one extra factor of 10 in this numerator than I do in this denominator. So these all cancel with all but one of the 10s from that numerator. If we look at the factorial, this is k times k minus 1 times k minus 2. Clear on down to times 3 times 2 times 1. This is k plus 1 times k minus 1 times k minus 2. All of the pieces that are multiplied together here are also in the chain of multiplication that's occurring right here. There's one extra piece that's present within this factorial that's not an element of this factorial, and that's the k plus 1 factor. So this entire factorial cancels with all but the top value of the factorial that's in that denominator. And then if you look at these x minus 1s, I've got k plus 1 x minus 1s being multiplied together in this position, and I have k x minus 1s being multiplied together within this position. I have one more factor of x minus 1 here than I have down here. Therefore, all of the x minus 1s here are going to cancel with all but one of the x minus 1s that are in this numerator. So let's think about what we're left with. We're left with a 10, an x minus 1 in the numerator, and a k plus 1 in the denominator, since everything from over here ended up canceling with something else. When I'm within a limit as k approaches infinity, 10 is a constant. I'm going to factor that in front of the limit. X minus 1 is now no longer affected by k, since this k is out of the exponent on that piece. So within the limit, x minus 1 is also a constant. I want to factor it out, but as I do, I need to make sure it stays inside the absolute values that the ratio test involves. So I've factored out the pieces that are unaffected by k, and then the limit as k approaches infinity is simply going to have 1 over k plus 1 inside of it. Put infinity there, this goes to 0, right? The limit as k approaches infinity of 1 over k plus 1, 1 over infinity, that's 0. So whatever is here times 0 actually gives me an answer for the limit of 0. This is actually kind of nice. This is almost a best case scenario when you're using the ratio test, because you've now determined that your limit of the ratio is always less than 1. What that means is that no matter what x is, this series is going to converge. Now, we don't know what function this series converges to. When we start talking about Maclaurin and Taylor series in the next few lessons, that's when we'll start to see kind of a relationship between the series and the function that it converges to. Here, we just know we have a pretty powerful relationship. Whatever function this series converges to, it's going to hold on the entire stretch of the x-axis, not just a tiny little portion of it. So the interval of convergence is all real numbers, and the radius of convergence is infinity. This was based at 1. I go up infinity units to the top value. I go down infinity units to the bottom value. Next problem that we'll check out is one that's a little tougher, because when we dive into the ratio test, you see we built the ratio here. We do the same sort of cancellation as we did in the last one. Not necessarily going to lead you through all of the algebra. If you want to pause the video and kind of reason out how the cancellation happens, you can. I factored out the pieces that remain inside the limit that do not depend on k. X had to stay in the absolute values once again. Inside the limit, I had a k in the numerator, a k plus 1 in the denominator. Limit of this is 1, right? Use L'Hopital's on this limit one time and you get 1. So this limit turns out to be the absolute value of x divided by 4. Ratio test says that we converge when this limit is less than 1. I need to know when that fraction is less than 1. So when I solve this, I change it to an equation. I solve the corresponding equation. I see my original inequality is not allowed to equal 1. So I have an open circle at -4. I have an open circle at +4. If I test a value from each section of the number line in the original inequality here, I'm going to see that the section that works is definitely what's in between -4 and 4. What this tells me is that my interval of convergence is -4 to 4. I know I'm going to converge in between those values. I know I'm going to diverge outside those values. In the initial video where we were discussing our first example of one of these power series that we applied the ratio test to, we said that the bad thing about an interval like this is that the ratio test is inconclusive at the endpoints. So at -4 and at 4, we need to analyze what's going on in a little bit more detail. So to do that, what we're going to do is we're going to take those endpoints. So we'll take 4 and we'll put 4 in place of the x, right? What happens when x equals 4? When x equals 4, do we get a series that converges? If so, we can include 4 within this interval. Do we get a series that diverges? If that's what happens, then we don't include 4. You already see the answer, so we're going to end up with a series that diverges when we put 4 in, and here's why. I put 4 here. 4 to the k divided by k times 4 to the k. The 4 to the k's are going to cancel, and what we're left with right here, that's the harmonic series. Harmonic series diverges. We know we don't converge at 4, which is why you see I did not include the upper value within that interval. What about -4? Well, when I put in -4, you want to be able to do the same sort of cancellation as we just talked about. So when I put -4 here, you benefit by breaking up that -4 to the k into an alternating term times 4 to the k. Because when you do that, you can still do the cancellation between the 4 to the k in the numerator and the 4 to the k in the denominator. This is also a series we know about. This is the alternating harmonic series. The alternating harmonic series converges. Therefore, I've included -4 since we get a converging series when we plug that value in place of x, but we got a diverging series at 4, which is why it's not included. So kind of a weird interval here. We could have discluded both. We could have included both. We could have had a situation where we included the one on the high end and discluded the one on the low end. So this analysis right here, taking the time to plug those values at the ends in and see what happens, that's really the only way to determine whether or not you can include either or both endpoints. This power series was based at 0. Our interval of convergence goes 4 units up from 0, 4 units down from 0. Therefore, our radius of convergence is 4. And then in the final example here, we'll look at this one. And in this one, again, I'm using the ratio test because right away, because of the inclusion of the k here, I know this isn't related to a geometric series. So diving right into the ratio test, again, you can pause the video to kind of confirm the cancellation. Once you've done the algebra that occurs immediately after building the ratio a few times, it becomes kind of repetitive. And then a similar sequence happens next. I'm taking out anything that doesn't get affected as k goes to infinity. X minus 5 is now unaffected as k goes to infinity, so I factored that out in front of the limit. I do have to keep it inside the absolute value since I don't necessarily know where x is. This limit is an easy one, right? Put infinity in place of k, and what you end up with is you end up with infinity. So I end up with this times infinity. I'm needing to know when this result is less than 1, because when this result is less than 1, that's when I converge. 0 times infinity is an indeterminate form when both pieces are within limits. 0, if we're there already, times infinity is going to give us an answer of 0. That distinction is important for me to make here because if this was approaching 0 and this was approaching infinity, that's indeterminate. I'm going to have to do some work with L'Hopital's rule to figure out what's going on. But if I am literally putting 5 in place of this x, 5 minus 5 is not approaching 0, it is 0. So if x is equal to 5, this product is less than 1 because the product is 0. Now, when I don't have this value fixed at 0, that's not going to be the case. So the interval of convergence here is actually pretty weird. It's just the x value of 5, and the radius of convergence is 0. So in this video, we've done 3 examples, and we've seen basically each of the 3 things that can happen when you apply the ratio test to a power series. You can either get a series that converges for all real numbers, right? We saw that, I believe it was with our middle example. Or no, that was our initial example. I'm sorry. Our initial example had that result. We could get a series that converges only at where the series is based. So a power series will always converge for at least one value of x, because when you put the value of x in where the series is based, you are guaranteed to get just 0 added together a bunch of times. So you are going to converge at the value of x where the series is based. The radius of convergence would then be 0. And then this third case is kind of worst case scenario. The interval goes up whatever the radius is from where the series is based. The interval goes down whatever the radius of convergence is from where the series is based. You may be including either or both of those endpoints. That's dependent on the analysis that we were talking about within that middle example. So the third situation is the most work. This is the best case scenario because you've developed a strong relationship between the series and the function that it converges to, that it converges for any value of x that you plug in. This is the weakest. These problems, you get to the end pretty quickly. The ones where you have an interval that's a finite stretch of the x-axis, that's the one that you're going to have to do the most work with. You've got to manually consider those endpoints, what's happening at them, can you include either or both, and then give the appropriate conclusion after that analysis has been completed.